Welcome to Foresight's Molecular Machine Group. I'm really happy today to be joined by Damien Sluysmans. I hope I'm not butchering your name. Before we launch into it, I want to have, I guess, two notes of, just like housekeeping notes. One is we're planning our molecular machines workshop for July 10 and 11, and that's coming up very soon. And we've already started reaching out to a few folks. But if you're working at the intersection of design, software, and molecular machines, that could be an interesting one for you. So just feel free to reach out to me. I think everyone here has my email address. And there'll be more info on that soon, but we're still in the background planning on this. So if you want to get early involved, then please feel free to do so. It's shared by Ben Reinhardt, by Adam Malveston and Will Shi, who I think presented a few times here already. So that's one exciting bit. Second exciting bit, our Feynman Prize applications are open. And so I would welcome all of you guys to nominate colleagues, to nominate yourself, and to nominate people that do fantastic work in molecular machines and towards Feynman's long-term vision of molecular
You can nominate yourself.
Yes, you can nominate yourself, Creon.
No, I won't do that, but that's interesting. Okay.
Yeah. Also, you have already received the prize, Creon.
I know I'm not into the self-nomination of myself. I'm just wondering if I'm into self-nomination by other people, but it's your show, so let's try it.
Okay, great. Well, I mean, look, this is one way to make it like ultra accessible, right? Like some people don't have another person that can nominate them, and then they have to reach out to another person to nominate them. And so, like, why not have everyone nominate themselves as well? I think that's totally entirely acceptable. Anyway, we can discuss more housekeeping later on. But for today, I'm very, very happy to be joined by Damien Sluysmans. He'll be discussing single molecule focus. Damien was a Foresight Fellow and is now a Foresight Fellow alumni. Very, very, very excited about what you're working on. I know that Anne-Sophie already received the Feynman Prize last year, so that's really exciting. And I'm really, really happy to have you join us. I can't wait for your discussion. I'll be in the chat. I'll share a few more of the resources that I just mentioned. And after a brief presentation, we're going to open it up for quite an open discussion with the group. Okay, Damien, the stage is yours.
Thank you very much. I'll share my screen. Okay, that's fine.
Looks great.
Okay, perfect. So good morning or evening, everyone, depending on where you are. So today I'm gonna focus on single molecule techniques. I wanted today to give you a brief overview of all the molecule that can be studied by AFM and optical tweezers in biology or in chemistry. So I will show some of our work in Liège, so the group of Anne-Sophie Duet, but also some other works that might be interested for you. So probably most of you know the AFM, but mostly for its imaging technique. So when you use the AFM tip to image a surface and get the topology of the surface, really a nice image of what is on the surface. But what we use here is the AFM for its force spectroscopy interest. So the idea is to trap a molecule between the tip and the sample, to stretch it, and to get the response, the force response of the molecule that is stretched here. I wanted also to introduce this other technique, which is mostly used in biology right now, which is the optical tweezers. So in this technique, you use optically trapped beads that's used here as anchoring point for the molecule that you want to study. It's just like the tip and the surface you have here. Here you have the beads, and they can be functionalized, and you can have a molecule of interest. And the idea is the same. It's really to stretch the molecule one at a time, and to get the force response and the dynamics of this molecule. Of course, both techniques are complementary here, depending on the resolution that you have. For example, for optical tweezers, you have a higher resolution with 0.1 piconewton, but the spatial resolution is better with AFM. So you have really complementarity between the two techniques. And what is mostly interesting is the stability in time. When you get a molecule that is attached between the tip and the sample, or between the two beads, for the optical tweezers, the stability is really better. So you can really stretch a molecule, keep it for minutes or hours if you're in the right condition, and really observe the dynamic of this molecule. So what we are doing is force spectroscopy. So it's approaching, so here, this is the example for the AFM. You approach the tip, try to create some interaction, and then you stretch on the tip, and you can have a molecule that is attached in between, and you get the response. So what we observe is the force versus tip surface distance. So the approach, then you push, and then you retract, and you see this particular behavior. The idea is really to probe one molecule. So most of the time you go, we go fishing. So we try to attach only one. So most of the time you have nothing during the retraction part. And this is really important. It's not like an artifact, or it's not something bad. It's really something good in order to be sure that we disperse all the molecules. They are not interacting with each other. So it's really a matter of drafting the right amount of molecule on the surface and have a right dispersion of them on the surface. And when you have it, when you stretch the molecule, you can, of course, apply some theoretical fit here on it, just like the worm-like chain. And you can check if you have only one molecule, and you can have some really special information about the behavior on the tension. So what we have here, it's really, we characterize the rupture force, the rupture distance, of course, which should be related to the system, but also we can have access to the flexibility of the system, depending of the system, if it's really flexible or not. Then the curvature that you see here on the curve will be different. So this is the main idea. Of course, you can have access to much more information, and I will give you some example today. So I will just have two parts in my presentation. The first one, of course, in biology, and I will discuss one example that we did in our group. And then the second part, which is really on chemistry, on synthetic molecules. So the difference here is when you look at biology, then you have to work in aqueous buffers. And in our group, we developed over the years an expertise in order to attach synthetic molecule and work in organic solvents. So historically, if we look back at some example of the stretching by AFM, you have access to this work by Herman Goeb. We did the stretching of the protein titin, and this protein is made of several domains, or Ig domains here, that can be mechanically unfolded. And when you stretch out the molecule, you pull on the molecule, you have, like, for example, this part, which is under tension. When the force is high enough, then you would break the intramolecular interaction that will maintain this domain folded. And then as soon as you reach this force, then it will unfold, and you will have another peak when you start stretching this central part again. And so by measuring the distance between the first point here, the point 1 and point 3, normally you have access to the delta length between this distance, so from this point to this point, and this point to this point. So you have an increased length that you can measure directly on the force curve. So it's not just looking at one peak and the force of desorption of your protein from the tip. It's also having some information about what is happening while you are stretching. And you can do that with much longer protein and have always the same length increase between the different peaks here. So this was a nice example of how we can really unfold different domains in proteins. And you can find now a lot of examples of this in the literature on DNA, protein unfolding, and so on. We can also do that in biology, but using optical tweezers. So by optical tweezers, you can pull on the bead, and you can see directly the force applied and the distance over which you apply this force by this change in the position of the bead. So this is how we can detect. It's not a deflection of a cantilever anymore. Here it's really how the bead is deviated from its original position. But you still have the same kind of profile here, so you can stretch it, and when you break something, you have a small peak. And the example here is, again, the unfolding of a protein. So you can unfold it, and you have an additional molecular extension, which corresponds to this delta X unfolding. But you can also have access with the optical tweezers to much more precise information. Here, if you imagine having like a DNA hairpin, you can really block the stretching at a certain external force and observe the extension of the system depending of the time. So you really observe how the molecule is behaving in real time. And you can see that you can have, like for here, it's just unfolded, folded, and you can have really this hopping phenomenon or this refolding, unfolding events. And this profile that you observe here will, of course, depend on the force that you apply and at which you block the whole system. And using that, you can have access to kinetics information or thermodynamics information, and then the energy profile of the system. Of course, you have a lot of work that's been done, especially by Michelle Wang at Cornell. She did a lot of work, and you can find some really interesting reviews about what she's been doing on biological machines, and it's really, really impressive using the optical tweezers. And you have different techniques here. I will not go into too much details about that, but this is really for your own information. So you can have really nice information about how this biological machine work in a buffer and at the single molecule level. Now I will talk about one of our recent work, which was on a bio-inspired system. It's a polymer, which is polybenzyl glutamate. So I want to talk about this in the biology part because it's really about what type of information you can get, because it's making it's folded in an helix, and the information that we get from this system is really linked to biological system, even if we are doing that in dioxin, so it's not in aqueous solvent. So the idea here is to have this polybenzyl glutamate, which will fold as a helix, and we have modified one hand for its gold surface anchoring, gold sulfur anchoring, and the other part is a back tether that would be attached to the DFM tip when we approach the DFM, and then we stretch the system. And this is typically what we observe. So here you have the first part, so it's the force versus distance. In the first part, you start stretching the back chain that you have here, and at some point you reach a plateau here, which is really characteristic of the system. And this plateau corresponds to the breaking of always the same type of interaction, so at the same force. So you break one after the other at the same force, and it will appear as a plateau. Since we don't have the resolution high enough, you cannot see the different peaks at the same force. But still, you can see that it's always the same kind of information of interaction that are broken. After that, you have the typical stretching of the whole system, which is this part unfolded and then the back chain. And so when we saw this type of characteristic profile, we analyzed the length of this plateau. And the length is not showing as a monomodal distribution. So you have different populations here in the distribution, which seem quite hard because we had always the same number of units. It's about 90 units of polymer here or amino acid. And so if we look back at what this different population means, so for example, for the 9.8, if you calculate the increase of length by the opening of one interaction, you can see that you have 45 amino acid in the system. For the 14, you have about 65, and the last population is 85. So it was quite odd for us that we could see this different population, even if the system has the same length. And so we looked back at in the literature, and we realized that when you look at helix, you don't have always this intact helix. If you look in the protein data bank, you always have some tertiary structure. And so you have a lot of work that's been studying, a lot of people studying what is the limit, so what is the critical length to see this helix as an intact one, or to see a tertiary structure. And in fact, you can see in a lot of papers that are mostly theoretical that you have a limit at around 20 amino acids, but it's never been proved like experimental. And so if you look here, it's always a multiplicity of 20 amino acids. So what we suggest here that we have, like, for example, here 2 helix that are with a kink in it. So in the tertiary structure, here 3, here 4. The only problem is that we don't see the single helix alone. The first explanation is that we have, of course, the exchange between the unfolded one and the intact helix with only one segment. So the idea is here, the system is not really folded that way, but you have different kinks in the structure because you reach this critical length for alpha helices, and then you align the system, and then you unfold this part. And depending of where you will stretch the system at different points, then you will have access to 1, 2, 3, or 4. And I will come back to the single helix later. So we also did what we call the pulling relaxing experiment on the system. The idea is to stretch the system, block the pulling. So for example, we can block here at 150 piconewton. And before we reach the point here where we lose the molecule, we reapproach the tip towards the surface. And during this experiment, so here in blue, you have the pulling, and then the relaxing is happening in red. You can see that with a small hysteresis, you can still see this plateau happening during the relaxing, meaning that when you release the tension, then the helix will reform directly after. And so this is happening in less than in half a second. It's really fast. Of course, for helices and the tension, it's normal, but still we can see this refolding that is happening. We also did some work where we wanted to add TFA, which will completely unfold the helix. Normally in solution, you put TFA and this is completely unfolded. Here, what we observe, if we add the TFA in the medium for the experiment, we can see 3 behaviors. The first one is the complete, so we have only single peak. In this case, it means like we don't have the helix anymore. So we don't have a small plateau appearing and we have a complete unfolding of the helices. We also see this plateau, but at much lower forces, meaning that the interaction are weaker in this solvent. And what we see also for some curve, it's the smaller helices that we could not see before. So of about 5 nanometers here for the plateau. So this is really the observation that was missing before. So this was the first experimental evidence that we can have really this limit, this critical length for alpha helices. And that's why I wanted to discuss that in the biological part, even if it's a bio-inspired synthetic system. So now I'll move directly to the chemistry part and to talk about different studies that we did and also some other groups. And the first one is the work by Hermann Goeb, who was the first one to show this with azobenzene, so polyazobenzene. And the idea here, it's really an idea that is not only for azobenzene, it's also for other systems. Can we really get a work being done by the molecule that we can detect by AFM? And so the idea was to have this polyazobenzene here between the surface and the tip. We can excite it and see the contraction of the system. And so the idea is schematized here. So we can have a system where you will load it. So you have a load on it, you can stretch it. And then you have a irradiation, and you can modify here the tether. And the tether would be, for example, here the azobenzene. And so you have a contraction, and this is a contraction we will talk about later. And this contraction will lead to a work being performed. So really a change from the energy from light to a mechanical world. And this is what they explain here in the the force curve. You can stretch a system, and then at this point you irradiate, and then the system will contract to this point. And here, the work that is measured here under the curve, it's the mechanical work by the optical contraction. And so this is the theoretical curve that you can have, like stretching the system, irradiating, and going back, and then you can like win some, gain some work being performed by the system. Now, if we move to more, I would say, strong interaction that you want to break, so really use AFM as a tool to break some interaction and get some information about the force to break these interaction. There are a lot of papers recently by Stephen Craig who show that you can really rupture some covalent bonds using the AFM. And from this, you can, of course, get the work. You can get a comparison between different interaction. So I invite you to look at those papers with a lot of different systems, which are really nice. So this is for breaking of covalent bonds. You can also make some covalent bonds. And for this, I will come back to the optical tweezers. This is the only work that's been performed for now for the creation of a link by optical trap and a single link at a time. So here it's a work by Zayed Galim from Boston. And what they did was to modify a bead here by two different systems here to create a click linkage. Of course, the difficulty here is really to find the two partners next to each other in order to create this bond. So here is the first example showing that you can create a single bond from two different beads. Now, of course, the next step, and this is something I'm really interested in, is really to use this technique in order to break and to do the reverse as Stephen Craig is doing. Of course, here you need to have something that is not covalent because you cannot reach as high a force as with AFM, but you can of course use this to investigate some non-covalent interaction. And this is really something I would like to discuss today. It's really probing a few or one interaction at a time, non-covalent interaction. And I want to start with this work of Guan in 2014, who used this system, which is two parts here that are linked with hydrogen bonds. And the idea, and this is really the nice idea here, is to have loops between these two parts in order to be able to break this part and then to see the reforming of these interactions. And so what they did was to have 8 units of this molecule, one after the other. So you have multiple units in series, and you can break this interaction one after the other. And so you can really have access to only a few interactions here in parallel. And you can also look at the evolution of the force depending on how fast you pull on the system. And this will give you information about the hydrogen bond that you are breaking. And so we wanted to study this, and this is a work that I performed in collaboration with Fraser Stoddart partly when I was with him at Northwestern, and I finished job here when I was in Liège. So the idea was to probe only one interaction at a time. So with a kind of host-guest system with a U shape here. So the idea is to have this molecule really attached between the tip and the sample. And in between, so in the solution, you can have a different compound that can come here. And here it will create some donor acceptor pi interactions. And so by pulling on the system, you will force it to open. and to be in this form, and we know exactly what is the distance in the closed form and in the open form. And so what we observe, and we did that for 3 different compounds, we observe not only a single peak with the stretching of the polymer, because here, of course, it's the long polymer, but in between you have, so here an additional peak, and this additional peak is due to the fact that you are breaking some intramolecular interaction. And depending of the molecule that you have here between the two piperidinium units, so you can have dimethoxynaphthalene, diaminonaphthalene, or dimethoxybisphenol. Of course, the force of interaction will be different. So we characterize the force of interaction and also the delta X, so the distance between the first peak and the second peak. And we could show that the distance between the two, it's always about the same. It's a little less than 1.5, 1.4. So it's about the distance that we have here. So it's correspond with the system. And the force here that you observe is in the same, so follow the same range as what we observe in the constants that we have in bulk, the association constant for the different compounds with the blue box. And so what we did was also to exchange to see if we could modulate the force. So we exchanged one compound by another, and we can see that before the addition we have a certain force, and after the addition the force is switching towards higher forces. So here it was an exchange from the first one to the third one, and we can see directly the shift in the force that we measure. Another one, and I will briefly talk about this one. It's an ongoing work with the group of Christophe Weder at the University of Fribourg. It's the same type of measurements. We wanted to look at not donor acceptor by stacking, but by stacking between the same units here, which is the beryllium diamide in between a loop. So if we see here, you have some interaction between the two units, and the idea was to break this interaction by DFM. So we have this design here, and we have the same for the optical tweezers that we are trying to work on right now. And this is what we observe. So we observe the same type of behavior, except that here, the loop that we have is much longer. Well, much longer, it's 5 nanometer, but it's something that we can see directly. And so we have a distribution here with which is centered about 5 nanometer, with the theoretical one also at 5. And so now we are trying to see if we can block this stretching by using the optical tweezers and get the dynamic of these two, of the interaction between these two. And the fact that we have the loop means that both partners will stay in close neighborhood. So we have much chances to recreate the interaction compared to other systems where you have two interactions that are attached to different beads or a tip and a surface. And when you break the interaction, they are far away from each other. So this is for the experiment with one or multiple non-covalent interaction at a time. I wanted also to give you a focus, but I will not spend much time on it, on the the molecular machines with mechanically interlocked molecules. But Anne-Sophie talked about that when she gave a talk for the Foresight, for the molecular machine group. So if you want to have more information about the Rotaxan work or the oligo-Rotaxan, when we search the system and open this really specific folding, you can also go back to her presentation, or we can also discuss about this later. So we have also some work on the cation, where we can see the difference of flexibility depending on the conformation. And the most recent one is the stretching of a synthetic oligoamide as a robust helix, and it's really the synthetic analogs compared to what I explained to you earlier. And we can see that with this system, which is really designed to have a robust behavior, you can have a much higher force, and the reversibility is extraordinary, and you can have really an elastic behavior with this system. The last one, of course, here is I have to talk about this. It's really an important work with rutaxane, but by optical tweezers by Borja Ibarra. So we did exactly the same as with AFM, but we can have access to much precise information. And this is what I like also with optical tweezers, is that you can have you can see here where the ring is positioned compared to the two stations here on this rutaxane. And depending of the external force, you can have you can really see the difference of population between these two stations and have access to the potential energy surface here. So the last one I want to discuss is the one that, so it's the manuscript is almost ready for publication. It's the tightening of a synthetic molecular knot. And it's in collaboration with David Lee at Manchester. So of course you all know this type of molecule where you have here a trefoil knot. And what we did was to attach this knot between an AFM tip and the surface. So here it's overhand knot because it's not completely closed. And the idea here was to see if we could tighten the knot more than it really is, and if this tightening was reversible or not. So we didn't know exactly what to observe in the force curve when we first started this project. And this is what we observe here. So we have this force peak with a small plateau, and this plateau has a distance of about, well, a length of about 1.1 nanometers. So it's really small. And sometimes with the noise that we have, it's almost impossible to see it. So we need to go into really flexible cantilever in order to see this small change here. But this characteristic plateau appear, so here it's in TCE, tetrachloroethane, appear at quite high force, 100 piconewton. And so in order to understand what was happening during the stretching of this knot, we discussed with some people in Bologna. So the group was Francesco Zervetto, and they did some simulation, so QC calculations here, by stretching the two parts here of the molecular knot. And they could have the optimized geometries and the energy, and this is what they show. So at some point here, normally you start increasing the energy when you put on the system, and at some point you have different, some kind of sawtooth pattern where the energy is almost stable for some time. And maybe I can show. Yes. So right here is a small movie where you can see directly the stretching. And what is happening here is that when you stretch on the molecular knot, there's one part that is sliding inside, because here you have the flexibility of the of different unit of ethylene oxide, and you can slide inside the knot's cavity. And this sliding here is limited by the presence of small naphthalene units here. And so the fact that we see the 1 nanometer sawtooth pattern comes from the fact that you have this flexible part that has the enough space to go into the knot's cavity. So you always see this 1 nanometer plateau, and sometimes if you change the solvent, so here in acetonitride, the plateau is at much lower force. And the fact that you have the plateau at much lower force means that it's less difficult to make it go through the cavity. And in this condition, you can see a second plateau appearing, meaning that the second part will also go through the cavity of the knot. And then, of course, what we were interested in was to see if the knot would come back to its original conformation or stay like this, like blocked. And the information I wanted to see also if the lutetium, which maintains the system in this original conformation, is staying around the knot, or is completely ejected in the solvent. And how can we say that? When you stretch the system and you tighten the knot, if the lutetium is ejected, when you release the tension, you will not have something that will maintain the knot conformation as it was before. So you will completely stretch the system, and the knot will completely unfold, if you want. And what we see in the in the force curve here is that during the pulling, you still see this small plateau, and during the relaxing, it appears again, and it's exactly the same. So you have almost no hysteresis, and you come back to the first behavior of the molecule that is in its original conformation. So here, the lutetium seems not to be ejected, and you still see the plateau, and you can do that several times, and you see the plateau in both cases. So with that, I would like to go to the conclusion. I hope it was not too fast with different systems, but the idea here was to show different single molecule focus, different molecules that can be studied by these two techniques. Of course, more so on the AFM, because it's more the chemistry part I wanted to talk about today. But with this technique, you can, of course, see the force performance and the dynamics of this system. Probably the mechanism for some system of, for example, for the knot, for the stretching on the force. And the idea would be to compare the systems of bio and synthetic systems, such as the helical system, which we have more biological one and a more synthetic one. And with that, I would like to thank, of course, the group, the nanochem group at the University of Liège, collaborators, the funding agencies, and thank you for your attention.
Wonderful. Thank you so much. Okay, lovely. You see a few clapping hands already. I'll add my reaction to it. Great. Thank you. That was quite the walkthrough. I'm really happy to hear about all the updates. I want to give first to a few questions, maybe of understanding. Does anyone have an immediate question of understanding here from the group? Feel free to go for it. Otherwise, I'll chime in with my questions. And as usual, the heuristic is that I'll start with questions. If you want to make me stop, just chime in with your own. Thank you so much, Damien. That was really wonderful. I think, a few questions that we usually try to ask, and I think that, would also be interesting for other people that, may just be entering the field to see really what they could plug in with is, whether you have any like long-term, not predictions, but at least like hopes for where this research could go. Like, why is it exciting, and what could be available in the long run? Do you have any ideas?
Yeah, I mean, we are always discussing with collaborators in order to find new systems that would be interesting to study by AFM, and we are always dependent of that. And we always have a lot of hopes, and we are talking to them and say, okay, what can you change? Can you change that? Can you change that? And we say, oh, whoa, don't go this far. It's always complicated. So it's always a matter of the information that you want to get and how far you want to go into, especially in the molecular machine system. I've always wanted to study. So when I was with Fraser, this daisy chain systems, which can have, so we always see the contraction. So how can we do to really have a system with different parts that will contract differently depending on the external stimulus? That is something that I'm really interested in. But of course, this is something that is difficult to synthesize. And with AFM and optical tweezers, it's not only the part that you want to study, it's also the attachment with the surface or the tip or the beads. And we always have a problem with this part. And I think if we want to move forward with this technique, at some point we will need to have like a universal way of attaching the molecules. But when we discuss with chemists, I would say with real chemists about this, it will of course depend on the system that you are studying. Yeah, I don't know if that's really answer your question.
Yeah, no, that was already quite very helpful and quite creative. I see Steve's hand up here, so I want to be truthful to making me stop talking.
Yeah, I didn't respond when you said a question of understanding because this is almost more of an idea. But anyway, when you were talking, first of all, thank you. It was an excellent summary of a lot of really useful, cool work. But you were talking about making a covalent bond mechanically, basically, mechanosynthesis, which is great. But then you said that you couldn't apply enough force to break a mechanical bond. I understand you've got other bonds that might go first, weakest link. But my idea was to use an STM tip or AFM, I suppose. But put an electrical field on the covalent bond that would weaken it and then mechanically pull it apart. Do you know of anyone doing any kind of work towards that?
No, I don't think so. So while you are putting on the system, apply. So yeah, apply. Yeah, I don't know if anyone has ever done this. I mean, you can break the problem when I talk about breaking the covalent bond. It's possible with AFM because the anchoring is really good, and you have a strong interaction with the tip and with the surface. The problem was with the work that I show with optical tweezers, and at this point, it's just like the bead will go out of the laser. And we lose the bead. For AFM, it's still possible, but and it's been done already to break this bond with AFM or STMT. But the idea of inducing this by changing, by electricity, I don't think it's been done already, and it would be really interesting in terms of responsive system.
I think it's been done with a single, like a hydrogen atom on a silicon surface or something, where you put an electrical field and it breaks the bond that way. What I was thinking about is
Sure, but
from the side, and then and the other reason I thought you didn't have enough force was, okay, so the optical beads are probably the limit, but you have a long chain of bonds leading to the one of interest, and it's always going to break in, presumably the weakest one of those. But yeah, the optical tweezers, of course, the weakest part of it. So anyway, that's an idea.
Steve, there's an electrochemical reactions like the Colby reaction, where you can take two carboxylates, put an electric current across them, and they'll both decarboxylate and form a carbon-carbon bond. So your idea is pretty neat if you can get the voltage right.
Right. And one of the variations on that is if you do it under in a fluid, you can get some pretty impressive electrical fields controlled in there, but there's other issues with being in a fluid, of course, but it also avoids maybe some of the issues with vacuum, and there's trade-offs there, but that's another area of investigation. I think it's worthwhile. Anyway, thanks.
Yeah, thank you. But I think your idea is good in the sense that we always want to add more external stimuli in this force curve, force stretching experiment. But it's always tricky to add some more information and an external stimulus. But this is something that we are working on to have this external stimulus, which can be light. It can be an additional chemical in the fluid cell, and yeah, I mean, this is something to have orthogonal stimuli that will change the behavior of the molecule while you're pulling on it. Then you have more variable, it's more complicated, but of course it would be highly interesting.
Yeah, more food for thought. All right. Again, if anyone has a question or comment. Oh, yeah, you go.
Thanks for your talk, Damien. It was really, really interesting. Just to kind of go back to what you said earlier at the end there, about a universal way of attaching things to your tips. I guess I'm a synthetic chemist. We're often pushing back on people, telling them what we can't do. If you were to ask the synthetic community, what would be the desired errata? What do you want that you can't that we can't do yet as far as synthetic links for picking molecules up, essentially, I guess.
I mean, we have the way of doing things that we have in mind already. What we want in terms of the tether, the length of the tether that we want, and when we start discussing with chemists, they're always asking this: how can we change the system so that you can study it? I was thinking more the other way around. Meaning that not changing the system directly, so attaching end groups with longer polymers and some reactive groups. So for now, we are working a lot with gold sulfur interaction. So we add a lipoic acid at the end that will attach to gold. But more in another way of having, it's something that I want to do with optical tweezers. You have your molecule, and I just say, okay, at the end, you add something to make a click reaction, and then we can make this attachment in situ. So not changing the molecule that would take a long time in advance, but in situ changing and having a method, a protocol saying, okay, you add this molecule, you have only the end group that had been changed, and then you can attach directly the molecule. And whatever the molecule you want to study, it's not really a matter of what we want for the end group of the molecule or what kind of tether we want, because we always use the same. But the problem is it's always taking much time to make, and it always changed the strategy from the beginning for the synthetic chemist. So this is, I say for now, it's not such a big problem. But if we want to move in having, I would not say high throughput, because this is not the way we want to work, but to have a lot of molecule that we could study, I think this is something that is missing in the field. So really universal way of working. And another thing that I want to discuss also, and maybe this is something some of you can help me with. It's not only the attachment on the surface, it's also the way the molecules are dispersed on the surface. Because for now, we lose a lot of time by going fishing and getting the molecule. And the idea would be to have a really precise surface with a nice protocol that say, okay, I can image, and I have the ASM tip for that. I can image the surface, and I can know exactly where are the small holes where the molecules are. And then I go with my tip and I stretch it. And every time I get the molecule, I can have maybe 2 molecules or 3 molecules in a hole, but this I can discriminate. But the idea here is right now we just have low concentration when we put the molecule on the surface. And we want to have something more precise. And this is more complicated because you need to have non-adhesive surface with some hole that's really small, so that you can have like 1 molecule, but not that high, because your tip should go inside and not having a lot of information with the surrounding. So it's more about the preparation of the molecule and the sample. And I think we would, for the future, we would gain a lot of time by working on that.
Cool. Just on that last point, could you do it the other way around? So you're saying put a molecule in a hole. Could you have a molecule on a plinth, like say a nanoparticle? And then, yeah, you could have maybe scan across the surface. You see with your tip, oh, here's a nanoparticle. That's where the molecules are. And then move into a different mode where you try and pick up the molecules from that little stool that it's sitting on. Did that help?
It's a matter of size, I would say. It depends if you are sure the amount of molecule that you have and what is the size that you're looking at. If at some point you use the nanoparticles, I don't know exactly which size we would need for that. And I don't know what's possible. And I would say we have to face also the interaction with the surroundings. So if you have something more on the surface, then you should take that into account while you putting on the molecule to see if you don't have any interaction of the molecule with the surface or with the nanoparticle. Maybe there's something I have to check about this. I haven't thought about this.
And the kind of last thing in relation to that, is there any work on applying or making use of say, enhancement of a local optoelectronic enhancement at the AFM tip to stimulate a reaction?
We haven't used that. I've checked, so I don't know actually. I have to check about that.
Cool. Well, just some random things that came into my head as I was thinking about these things.
You're getting an entire laundry list of things to do. Well, that's all good stuff. Okay, great. Steve, you go.
Thank you.
One of the things that came up when you were talking about the lutetium compound was that because you've got a knot, you've got the complicated three-dimensional structure that can, even if the lutetium atom pops out, it's still got something to bind to, and it may go from a tri-coordinate to a di-coordinate to a monocoordinate kind of a system. And so what would be the possibility of studying it with a crown ether, for example, in the solvent with it, where you could have that lutetium actually leave the structure, and you could then study that dynamic to see how that alters it. And by having different size crown ethers, one would have different affinities for the lutetium atom that could then allow you to potentially balance that addition subtraction dynamic.
Yeah, exactly. This is actually ongoing work. It's really something that we want to do to really force the extraction of the lutetium. The problem is the first test that we did was to add this this other molecule. I don't remember exactly which molecule we used. I should check, but another molecule that will coordinate this lutetium to have the lutetium out of the nut. If you do that, the only problem, you cannot just do that when you have a molecule between the tip and the sample and then inject and remove the lutetium. You have to do that in advance. So you have to have a solution with the molecule that will eject the lutetium. And if you do that, then the knot will completely unfold before you start the experiment. So the problem is, and we see that when we have this type of molecule, or for example, we did that in DMF where you break the interactions, and so in DMF the lutetium can really be expelled, and then the loop will the knot will completely unfold, and you have only single chains in solution. And so when you stretch it, you don't see this small plateau anymore. You see only the stretching of a polymer. So it's possible to eject it chemically, I would say. The problem is you cannot expel it or eject it while you are doing the experiment.
I was thinking of more of a competitive effect where you would have like a temporary docking station where let's say the crown compound wouldn't be strong enough to tear the cation out of the knot. It would just allow it to reduce the coordination that would be with the knot by another level.
So change the chemistry of the system in order to have that.
Yeah, so you have something competing with the coordination complexes with the knot structure. I was also wondering if you had considered, looking at the click chemistry dynamic in series of force equations by, for example, having each click reagent, as you're bringing them together, to use some kind of a charge differential so that you'd be able to control how they would approach each other. And so you might have a positive charge on one and a negative charge on the other, so that the tails that you would be using would be stretched.
Yeah, I don't think for the experiments we are doing, I don't think this is possible, because when we have some experiments where we have the tip that is functionalized and the surface is functionalized, and we try to approach them to create the interaction. So we have this type of experiment. The only problem is the geometry to make the interaction. And for that, if you just approach the tip towards the surface and you stop a few nanometers before, or just 1 nanometer, you will not have the interaction. It's just a matter of statistics. And what we are doing right now is just pushing on the sample to make sure that we create the interaction, and then we start pulling to break it. But to have, like, in the right position, the right direction, and wait enough time to create the interaction, it's really tricky, and for us, it's not possible to have this. Even if you have something that is really that is not flexible, if you have tethers that are not flexible and you force it, you don't have the resolution high enough to make sure that you have the two partners that will make the interaction during the force curve. So this is really tricky to make and break the covalent bonds or an interaction by functionalizing the tip and the surface for the different partners.
What about using ozone and studying the dynamics of ozonolysis to have a double bond fatty acid stretched, and then have ozone gas attach it, where you're seeing a rearrangement, a multi-step rearrangement where the oxygen attacks the double bond and you get 2 electron transfers and it forms a ring system. That might be analogous to a click reagent reaction.
Yes, the promise here with this type of reaction is not only the time scale at which it's happening, but also the length that is revealed during the experiment. And here it's really small. And so you will not be able to know exactly where it will break, and then stop the breaking and then relax the system. So I think it's just a matter of the resolution here in the Z direction while you are pulling. But I understand the idea. It's really nice. It's just that we need to figure out a way to look at this system. I would say by breaking sequentially the different part of the interaction, and here it's really the resolution that is the limiting factor.
Wonderful. I hear a nod. Okay, great. Ted had another question, but he likes to keep the schedule, so we're 1 minute beyond now. If you have 1 minute to still spare, I would love to hear from you. If people are now excited, what can they do to help you work along and to support your research? Is there any this is like a shameless plug moment of just like, what would you need to be able to do your work better?
Sorry, can you? I was cut with the Wi-Fi. I could not hear.
Sorry, I was saying, if this is a shameless plug moment, what would be one thing that people could do to help you work along or to help research in your field along?
Synthesize more molecules. I would be brief about that. I mean, I love this. Something I did not talk about today, it's really the out of equilibrium systems and the system that can for the ratchet, for example, the ratchets are really amazing, but it's really complicated to do. So if you want to synthesize this, and I can work on that for AFM or optical tweezers, I would be happy to work on that. It's really something that I'm really a big fan of.
Okay, wonderful. Then we leave it here. Thank you so much for joining. It was really, really great to have you, and what a fantastic presentation. Thanks everyone for your great questions. We're now 2 minutes over time, but I think it was worth it. Thank you, Damien. Very, very excited about your research, and I hope to see you in the next meeting.